Today we're going to be talking about a project I've been working on for since about March of last year, called Valkey-Timeseries. Just by way of introduction, who am I? My name is Clayton Collie. I'm an independent software engineer. I've been contributing off and on to open source for a bit. And now I'm happy to be a contributor to the Valkey project. So what is Valkey-Timeseries? Valkey-Timeseries is a high-performance, scalable time series database built as a module on top of Valkey. And one of the things that we're trying to do with Valkey, one of the things we eventually hope to go beyond it, but one of the things we want to do is also to be a drop-in replacement for RedisTimeseries. Oh, there you go. So, just general information. What is a time series database? A time series database is a type of database designed specifically for storing and querying data that's indexed by time. It's used in various industries, IoT, fleet management, healthcare, banking and industry. Yes.
Zoom in.
I'll zoom in. I'm blind. I'm blind. Oh, fantastic. Oh, I can see. Basically, a time series measures metrics. I'm sure most of you here would be familiar with observability platforms like Prometheus. So this should be pretty straightforward. So in terms of metric, a metric consists of name, your metadata, timestamp, and value. And again, like I said, you can find time series database in all kinds of places. Like I said, environmental data, application analytics, financial analytics, IoT and sensor data, monitoring and observability. Just a quick question. Has anybody used RedisTimeseries in the past? Okay. For those of you who haven't, I'll just run through a really quick introduction. Essentially, in Valkey-Timeseries, you're able to add a sample to a time series by the ts.add command. In this case, we're monitoring the temperature of our living room. And so what we're saying is the very first argument is the key, which is the living room. The second command is the star, which basically means the current time or now. 25.7, pretty warm, is the temperature that we're adding to that particular key. Next, we're going to add a measurement for the bedroom. Similar thing, we have the key, we have our timestamp, we have our temperature, and with a key we can add metadata. In this case, we're indicating that that the room is bedroom and it's in the it's in the main building. Similarly, if you can put data in, you can get that data out. And so the main The main command to get data out of a single series is ts.range. In this case, we're looking at the living room, so ts.range, temperature, colon living room. In RedisTimeseries, the negative represents the earliest timestamp. Plus represents the latest timestamp. Count is the amount, the upper limit of the amount of samples that you return. And one of the good things we can do is we can aggregate over the items that are selected in the range selection in the minus and plus. So whatever data gets selected within that range, we bucket it into, that's an hour. We do an hour bucket and we average within that hour bucket. Next we have ts at mrange. Mrange is a command that allows us to use labels to query across time series based on the commonalities between labels. So in this particular case, we're just trying to get all the data from rooms in the main building in this particular case. One of the compelling use cases for Valkey-Timeseries is downsampling essentially, where what you do is you, in a lot of cases, what you want to do is, in addition to storing raw data, is you also want to store summaries of those data of that data for quick analytics. So the way that you specify that you want to create a downsampling is you use ts.create rule. You give it the name of the destination time series. Oh, I'm sorry, this is the source. The second here, the ts colon living room colon 1H, you're essentially telling it that you want to create a compaction of 1 hour. Basically, you want to bucket your input samples into buckets of 1 hour, and you want to aggregate in 1 hour buckets. Basically, every aggregation is 1 hour. You're basically creating 1 hour buckets, where the value in the bucket is the average over that time span. When you create a compaction, essentially it just creates a regular time series that you can query just like any other time series in the database. So in this case, we're just getting in the 1 hour aggregated time series, we're just getting all the values in the data set. That's a little bug. This is a little bit complex, so I'll skip it. But essentially, you get the idea. What you can do is set up here. Essentially, what we're doing is setting up multiple compactions so that every time data comes in for the living room, we just create aggregations at the 1 minute, 1 hour, and 1 day granularity. The delete from a time series is just ts.del. And so these are just the very basics that you can perform on a time series. So although Valkey-Timeseries is intended to be a drop-in replacement for RedisTimeseries, we have put in a lot of work in terms of performance and also in terms of some quality of life changes. So I'll just outline some of these here. The first is active expiration, which essentially means that we have a process running in the background that automatically clears out stale data For time series data, we can specify a retention period. So in Redis time series, as far as I remember it, GC basically only happens. It basically happens lazily. So you don't clear out stale records unless you actually access the time series. What this does is it uses cron jobs in the background to actively clear out expired samples. Number two is multi-DB support, where a time series can be created in multiple DBs with proper isolation. So this includes support for swap DB. So for instance, you can set up a DB, do all your work, and just do a swap DB to make it the primary. And that works perfectly fine. Rounding. One of the things we can do, if you take, for instance, if you have IoT sensors that are measuring temperature, unless you're in a very specific industrial use case, there's generally no need to store more than 2 decimal places. And there are other cases like that where you don't need so much precision. So what we can do is specify up front that either that we will truncate either by decimal place or significant figures. The upshot of that also is that because of the compression that we're using, we could in a lot of cases can help in terms of compression. Dependent compactions. This really only works for metrics like counts. So for instance, you can specify a compaction in terms of another compaction. So for instance, if you have visitor counts for 1 hour, you can base the visitor count, the one-day visitor count, based on the 1 hour visitor count. It's just a way of allowing you to set up dependent compactions. Compaction policy filters. One of the limitations with RedisTimeseries is you can specify compactions in your config file. The only issue with those is they apply universally to all compactions. There's a problem with that in that there are certain compactions that don't make sense. For instance, for a counter. For instance, I doubt many people want to store what the minimum value of a counter is as a compaction. It generally doesn't make sense. So what you can do is you can actually specify the keys to which a compaction applies. And so when a compaction is created on the fly, it will only apply those compactions to what matches the regeds. Query filter enhancements. I spent a bit of time over the past year working with platforms like Prometheus and Victoria Metrics. And so one of the things I've done is, in addition to what currently exists, we can now use Prometheus. Basically, we can use Prometheus selectors for querying our time series. It more or less matches Prometheus. As a matter of fact, in the repo, I pretty much used their test suite. Of course, it's modified to fit within the project, but what this basically means is we can use Prometheus-style queries to query the time series. We also support OR matching in addition to AND matching. So in this case here, you can see our example here where we select this particular time series where job is app1. Well, basically a combination of these two different filters. Another quality of life change is that since we have a secondary index, we're also able to query that index. So, for instance, if I have a series of services running across different regions, and I want to find what are the services, for instance, that are running in US East 1, I can make a query and say, give me the label values of everything where region equal US East 1. The other thing that we can do, there's a stats command that gives us essentially an overview of the cardinality of the labels in the index, so that we can see which labels are more frequently used. Developer ergonomics, just quality of life changes so that we can have things like this, like relative durations and timestamps. The big feature in this particular release is also joins. There are different types of joins, and part of the motivation, well, it actually started with as-of joins, which we support. So, for instance, if you have a trading platform with buys and sells, and the timestamps don't exactly match, you can do an as-of query and specify the tolerance. So you can say, match all buys and sells within the nearest 2 milliseconds. And in addition to that, we have basically reduction. So for instance, if you want to find the spread, you can say match buys and sells within 2 milliseconds, and you can specify a reduce as a sub, which basically subtracts the value of the buy from the sell and return that value. So in terms of implementation, the main data structure is a time series that's divided into a series of chunks. The chunk is the basic medium of storage, and it basically offers a compromise between compression and latency. So essentially, if you have a bigger chunk size, then you get better compression. But on the flip side of that, your latency is a little bit worse because, unfortunately, to get a range within a chunk, you actually have to iterate through the chunk. The good thing is when you set up a time series, you can specify what the size of your chunk should be. Then, as mentioned before, time series also has labels, which is your metadata about the time series, and each label is basically a key value pair. And if you're familiar with Prometheus, it basically functions in the same way. Okay, just a second. Oh, where am I? Oh, sorry. I'm not looking. Just a second. So let's talk about some of the optimization work. Yes? On to, just a second. Sorry about that. Here we go. Okay, so let's talk a little bit about some of the performance and memory saving features that we use. Number one is that for the labels we use string and turning. For the most part, labels are string key values are heavily reused in time series. So for instance, if I have series across different regions in AWS, it's quite likely that I have 20 up, like thousands in one region, thousands in another region. And so simply by the nature of observability, those labels tend to be duplicated. So what we do is, whenever a label is created, we check first to see whether or not that label already exists. If it doesn't, we create it. If it does, we just simply point to the existing label. It's reference counted, so it's automatically cleaned up when the last time series uses it. But it can dramatically reduce memory usage in terms of labels. Then let's talk about indexing. So in order to query, we have a secondary index, basically an inverted index that's implemented as an adaptive rated tree. At the top level, it's an adaptive rated tree where the leaf nodes are actually roaring bitmaps. We also have bidirectional mapping between the ID, a U64 ID, and the Valkey key. So essentially, every time series has an associated opaque 64 bit ID, which is actually what gets stored in the inverted index. And because we're using roaring bitmaps, it's actually pretty performant. So basically, how we index is the basic indexing scheme is key, then the separator, and then the value. That gets inserted into the rated tree, along with the ID of the time series that it belongs to. And so let's just give a very simple example. Let's say we have this time series here, and its ID is 10. What we do when we insert into the index, first of all, if anybody's worked with Prometheus, you'll know that the name, basically, the key associated with names in Prometheus is this underscore, underscore, name, underscore, underscore. And so what we do is we insert name equal latency, and then for that particular branch, we insert the ID of the time series. We then move on to region equal US East 1, EU East 1, sorry. So we create this branch, and then we insert it here, sorry. Similarly with ENV equal dev and service equal billing. Now if we go to the next slide, we do the same process with the other, with two other time series. And so if we want to query, so for instance, if we want to query for all time series in the EU, whatever EU region, with env equal dev, we simply look up in the tree, so region equal EU. And again, because we're using an adaptive rated tree, we can do easy prefix searches. Sorry. So because we're using a rated tree, we can do easy prefix searches. So once we do a prefix search on the prefix search here, we just iterate through all nodes that starts with EU. That's this match here. And so we get 10, 20, 30. And then for env equals dev, we have we have two items here. And all we do is we do an intersection and we get the IDs of the corresponding time series. Hold on a second, there's more. What is going on? Oh, I'm sorry. I clicked on the image, that's why. So here is where we gain massive performance. One of the things we do in Valkey-Timeseries is we extensively use parallelization. And this is especially useful where we have queries that span both over chunks as well as over time series. So in this tour example, we're doing an M range over events where metric equals CPU and doing an aggregate with a bucket of 1 day. So what we imagine here is we're trying to average over a quarter. And we're imagining here that each chunk basically holds the data for 1 month. Because of how we implement it, we can actually fan out, at this particular level, it's the data fetch. So essentially, we fan out the data fetch to as many cores as we have in our machine. As soon as that comes back, we also fan out here, so that we also run all the we run the aggregations in parallel as well. Oh, I'm sorry. So next, yes? Oh, what time is it? No, interrupt me at any point. Interrupt me at any point, I'm sorry.
Seems like there's a question a little bit above where
Sure.
you were talking about the labels. So Martin, you had a comment there that seems like duplication. Do you want to ask?
Yeah, Yeah, I mean, we can leave the question till the end, but the specific question is that I can see the lookup advantage of this, right? But do you have a lot of memory overhead with these kind of indexes?
No, the good thing about rated trees is it uses prefix compression. So, for instance, if you look at the tree, so you have a node at this level. However, the key is actually encoded in the path and not in a node. And so what happens when you search in a rated tree, basically it does a longest common prefix. And so what you're actually seeing here is this is just for ease of visualization, but that's actually not stored. That's actually not stored. Basically what happens is the path is stored in the edges. And the other thing that happens too is that generally with rated trees is you won't have a node that has only one child. So yeah, so it'll consolidate a node if it only has one child. So this is it's actually pretty efficient because, so for instance, if you take into consideration these two, basically this isn't duplicated. Like none of this path data is duplicated. Right. So it's very efficient.
Yeah. And you were also talking about how the compaction comes from the labels. There's a separate dictionary that has that. So you don't have the overhead per sample.
Yeah.
You have 15 more minutes.
Okay, yeah, sure. Okay, so ingestion. One of the things we do, so in Valkey-Timeseries, there's an MAD that allows you to add multiple samples at a time. And the interesting thing about it is you can add it across multiple series. What we do here is we basically batch and group. So for instance, we group all samples going to a particular series. And within the series, we also batch all samples that belong to a particular chunk. And then what we do with that chunk is we do a merge. Rather than single inserts, we do a merge. This is particularly helpful because what happens is, in the general case, we use compressed chunks. And because otherwise what would happen is you would actually be rewriting the chunk for every insert. So what we do is we take all the samples that belong to a particular chunk, and we do a single write at a time for however many samples belong to that particular chunk. That's at the lower level. At a slightly higher level, we group those batches by time series. So we parallelize those. The similar thing happens with downsampling. So for instance, what happens internally is for every time series, so a time series can have multiple downsamples. So essentially what we do is kind of like I guess it's more of a breadth first search. So at every level we collect all the children. We collect all the children from a time series and run all the down samples for that particular parent at the same time, and then we just recurse and do it all again. Is that it? Okay, I think that's it. There's a little mismatch between what's on GitHub and what's on my machine. It's not much. It's just the address to the repo. So if anybody has questions, I'll just entertain questions now.
Do you have a demo?
I do not.
Okay.
I do not.
Anyone else?
Thanks. I guess I got two questions. The big one obviously being what's the RedisTimeseries compatibility like?
So it's compatible on the API level. The internal, of course, the internals are ours.
Are you complete in terms of compatibility or not yet?
Yes, there's only one thing that may be an issue, but that's nothing. Well, actually, no, because we don't claim to be RDB compatible. So we will. So the API is basically one-to-one.
Nice. Good job. Second question was when you create the aggregations, can you set a start and end time? I can't remember. Or can you just set a period? I can't remember off the top of my head how that was.
You mean when you're setting up downsamples, setting up compaction?
Aggregations, right? So you're saying last hour, yeah.
No, when you run them, you can do whatever. You can give it any range you want. When you set up compaction, no.
No.
Yeah. No, but one of the interesting things is, and I've thought about this. I don't know if we need it. One of the things with RedisTimeseries is, if you set up a compaction, you don't get backfill. And so if that's something that's useful, that's something we can build in.
Any other questions?
Questions? So just to give a kind of like a status, as far as what I intended for first release, basically is feature complete. There's still some testing that needs to be done. One of the things I'm not satisfied with is the clustering code. There is clustering code, but I don't like it very much. So that's what I'm going to be working on in the short term.
I think I do have a question about that. So whenever you do have a cluster and there's a request that touches multiple series on different shards, how does that work?
So what we do is we take the request, we shoot it out. Basically, there's a scatter gather process. We take the request, shoot it out to the different shards. There's a count. There's a count of nodes. So basically, when we shoot it out to the cluster, we maintain a count of the nodes that we've sent it to. And as the request comes in, we we count down the counter. And at the end, there's a callback that gets called that basically coalesces all the data from the nodes and then spits it back to the client.
Thank you. I do have a question for the group. Does anyone have any time series use cases? Fraud detection?
Energy makes a lot of use of time series because currently we don't have batteries big enough. So in order to supply electricity to consumers, you have to make predictions what we're going to use. So we use all the consumption curves from previous years plus weather predictions and all that. So it's lots. I mean, my first question to your time series was how much can you cram in the space? Can you compress them? Lots of stuff.
So, like with all things, compression, it depends on the nature of your data. So essentially, if you're generally speaking with time series compression, it's generally done by deltas. So, for instance, if you consider something like temperature doesn't change appreciably. And so compressing temperature data just yields very, very high compression generally. If you have data that has a high amount of precision, then less. But it depends a lot. It depends a lot on the data itself. But generally, the compression that we use does fairly well. It's fairly well in the general case. One of the other things that I'm experimenting with is there's another Rust-based library for data compression that has very, very good. It's an adaptive compression, so basically it adapts to the data that you give it, and so that has promise of giving us better compression.